I am Dr. Mamta Bhusry from Ajay Kumar Garg Engineering College, Department of Computer Science and Engineering. This is my second lecture on concurrency control techniques in database management systems, and in this lecture I will cover the timestamp ordering protocol. The books, as I have already told you, for this topic are Database Concepts by Koth and Fundamentals of Database Systems by Navathe. In my previous lecture, I have already covered the locking techniques, that is the two-phase locking protocol and the multiple granularity protocol. In this lecture, I will do the timestamp based timestamp ordering protocol. The concurrency control based on timestamp ordering ensures serializability by creating a serial order among the concurrent transactions by assigning to each transaction a unique timestamp. Now, what is a timestamp? A timestamp is a unique identifier created by the DBMS to identify a transaction, that is, it is the time when the transaction enters the system or is started. We will show or refer to the timestamp of the transaction as TI, which means TS stands for timestamp and TI is the transaction which we are talking of. Timestamp values, they are assigned to the transaction in the order in which the transaction enters the system. So, we can say that the timestamp is the starting time of the transaction. In database systems, the timestamps are assigned to transactions in two ways. One is using the the system clock, and it gives the current date and time value of as the timestamp of the transaction. Second is the logical counter, which is incremented each time its value is assigned to the transaction, and here the timestamps, they are given as numbers 1, 2, 3, 4 and so on. Now, we talk of the older and the newer transactions. So, let us consider that we have the transactions Ti and Tj are two transactions such that Ts is the timestamp of the transaction Ti, Ts is the timestamp of the transaction Tj. Then if Ts of Ti, that is the timestamp of the transaction Ti, is smaller than the timestamp of the transaction Tj, then we say that the transaction Ti is older than the transaction Tj, or the transaction Tj is younger or newer than the transaction Ti. So, the transactions with the smaller timestamp, they are considered older than the transactions with the larger timestamp. Now, the timestamp ordering protocol, also called the TSO protocol, orders the transactions based on their timestamp values. A schedule in this case is said to be serializable when the equivalent serial schedule has the transaction in the order of the timestamp values. To implement the timestamp ordering protocol, we will say that each data item associates with it two types of timestamps, the write timestamp and the read timestamp. The write timestamp given as this WTS X, where WTS is the write timestamp, X is the data item, is the largest timestamp of any transaction that executed a write X successfully. That is, it is the timestamp of the most recent transaction that executed the value of updated the value of X. Read timestamp of X is the largest timestamp of any transaction that executed read X successfully. the read and the write timestamps, they are updated whenever a new read X or the write X instruction is executed. In a TSO protocol, a conflict is said to occur when an older transaction tries to read a value that is written by a younger transaction, or an older transaction tries to modify a value that has already been read or written by a younger transaction, and when conflicts occur, the transactions are forced to roll back. Both these actions, they indicate that the older transaction was too late in performing the required read or the write operations, and it could be using the values from different generations for different data items. So, the basic timestamp ordering protocol is as follows. Whenever a transaction Ti needs to perform a read queue or a write queue operation, then it will request permission from the system to perform the operation, and the system will handle the request in the following manner. We will consider two cases. First, when Ti issues a read queue, where Q is the data item, and second, when Ti issues a write queue, where Q is the data item. First, let us take up read queue. Now, when Ti issues a read queue, if the timestamp of Ti, that is the timestamp of the requesting transaction, is less than the write timestamp of Q, which means the timestamp of the requesting transaction Ti is less than the timestamp of the transaction that last updated the value of Q. Or in other words, we can say that an older transaction is attempting to read a value of Q that has already been written by another younger transaction. So, in this case, the read operation is rejected because there is a conflict and Ti is rolled back. The second case that can happen when Ti issues a read queue is that Ts of Ti is greater than equal to write timestamp of Q, which means a newer transaction is attempting to write the value of Q. So, in this case, the write operation is permitted and the in this case the read is permitted and the read timestamp of Q is set to maximum of timestamp of Q or the timestamp of the transaction. The second case, like we said, was when Ti issues a write queue operation. Now, here if Ts of Ti, that is the timestamp of the transaction Ti, which is attempting the write, is less than read timestamp of Q. This means that Ti, which is in this case an older transaction, is trying to write a value that has already been read by a newer transaction. So, again there is a conflict. This is not permitted and the transaction is rolled back and restarted later. Second case can be when Ts of Ti is greater than read timestamp of Q. That is, the timestamp of the transaction that is requesting the write is larger than, or we say the transaction is newer than the transaction that last read the value of Q. Hence, Ti is permitted and the write timestamp of Q is set to the timestamp of the transaction. The next case is when Ts of Ti is greater than write timestamp of Q. That is, now a newer transaction is trying to write the value of Q and hence again this transaction is permitted and the write timestamp of Q is set to Ts of the timestamp of the transaction. Here the timestamp of Ti is less than timestamp of the write timestamp of Q. That means an older transaction is now trying to write the value of q which has already been written by a newer transaction. Hence, again the write operation is rejected and the transaction is rolled back. The timestamp ordering protocol ensures conflict serializability. Deadlocks, they will not occur under the TSO protocol because a transaction is never required to wait. Transactions, if there is a conflict, are rolled back, but starvation may occur if a transaction is continuously aborted and restarted again and again. That is, it does not get a chance to execute. Now, let us consider an example where we have the transactions T22 and T23 such that timestamp of T22 is less than timestamp of T23. That is, T22 is a older transaction as compared to T23. We need to check if this schedule is possible under the timestamp ordering protocol. Let us do it. So, we have T22, T23 and we see what the timestamp ordering protocol, how it executes. So, here read A, this will be executed and the read timestamp of A will be set to timestamp of the transaction T22. Read again A again is okay and the timestamp, read timestamp will be set to timestamp of T23. Write write here. Now, let us see whether this write can be executed or not. This write can be executed because now T23 is a newer transaction as compared to the transaction T23 is the same transaction as which has last read the value of the data item over here, and write timestamp of A is set to timestamp of T23. Now, read B is okay over here and the read timestamp of B is set to timestamp of the transaction T22. Read B again is fine. Read timestamp is set to timestamp of the transaction T23. Write B is okay because again in this case the same transaction T23 is trying to write to the value of the data item B which has been read by T23. So, we say that this schedule is possible under the timestamp ordering protocol. Now, let us consider what the Thomas's write rule is, which is a modification of the basic timestamp ordering protocol, but it does not enforce conflict serializability like the TSO. It allows for greater concurrency. It allows view serializable schedules instead of conflict serializable schedules. Let us consider this example now. If we apply the timestamp ordering protocol to it, we see read q is permissible and the read timestamp of q is set to the timestamp of the transaction T1. Now, when we come to wq, now it succeeds because a newer transaction T2 from here, a newer transaction T2 is attempting to write to the value of the data item q as compared to the older transaction that had read. So, the write timestamp of the write timestamp of q is set to timestamp of the data item is set to the timestamp of the transaction T2. Now, let us check the wq over here. Now, this wq is rejected because an older transaction T1 is trying to update the value of q that is already written by the younger transaction, and hence this write q is rejected. The transaction is rolled back in this case. So, we see that this schedule is not possible under the timestamp ordering protocol. But also we observe that this rollback, that is the rollback of WQ over here, was not necessary because the value of Q which is written by T1 will never be read. Why? Because any transaction which is, let us say, older than the transaction T1, any transaction Ti with timestamp TSIT less than TS of T1, that is older than T1, that attempts to perform a read Q will be rolled back. Why? Because timestamp of Ti, any transaction which is before T1 will be older than the write timestamp of Q. So, it will be rolled back as per the TSO protocol. Any transaction Tj with TS of Tj greater than timestamp of T2, that is any transaction Tj that occurs after T2 will read the value of Q which is written by T2 instead of reading the value of Q written by T1. So, these observations they lead to the modified version of the timestamp ordering protocol, which is called the Thomas's write rule. The Thomas's write rule ignores the outdated obsolete writes such as these writes, and the protocol rules for the Thomas's write rule, they are for the read operation are the same as the TSO protocol, whereas for the write operations the protocol differs. Now, the Thomas's write rule for the write operations is as follows, that is, if TS of Ti is less than read timestamp of Q, that is a older transaction is trying to write a value that has already been read by a younger transaction, then the value of Q that Ti is producing was previously needed, WQ is rejected and the transaction is rolled back. This is the same as the timestamp ordering protocol. This is where the Thomas's write rule differs, that if TS of Ti older transaction is trying to update the value that has already been written by a newer transaction, then Ti is attempting to write an obsolete value of Q, hence it is ignored. In the TSO protocol we discussed that this is rolled back over here, but according to the Thomas's write rule this is ignored. And in all other cases like the TSO protocol, WQ is executed and the write timestamp is set to the timestamp of the transaction which has updated the value. Advantages of the TSO protocol we have already seen. One is deadlock free. Why? Because no transaction ever has to wait, and there is freedom from the locking overhead. Since there is no locking involved, hence freedom from the locking overheads. Disadvantages of the TSO protocol: cascading rollback can occur, that is, if a transaction fails and other transactions have already read the value updated by that, then the further transactions will also be rolled back. Non-recoverable schedules can happen. There are chances of starvation if the transaction is rolled back again and again, and when a transaction is rolled back, then the work performed by it is undone. This requires additional work, hence bringing down the system throughput. Now, let us take this example where we will check if the schedule is possible under TSO protocol and under Thomas's write rule. The three transactions are T1, T2 and T3 with timestamp of T1 less than that of T2 less than that of T3. First, let us apply the timestamp ordering protocol. So, WA over here is executed and write timestamp of A is set to the timestamp of the transaction T1. Here read A, since the timestamp of T2 is greater than that of T1. So, T2 is a younger transaction, hence again this is executed and the timestamp of read timestamp of A is set to the timestamp of T2. WC is again okay, and write timestamp of C is set to timestamp of T3. WB is okay, write timestamp of B is set to timestamp of T1. Now, let us look at WC, that is write C. Now, this write C according to TSO protocol will not be permitted. Why? Because now C has been updated by a newer transaction and the transaction T2 is trying to override the value of C that has been updated by a newer transaction. So, under the timestamp ordering protocol, this will not be permitted and T2 will be rolled back. Hence, we say that this schedule is not possible under the timestamp ordering protocol. Now, let us consider the same schedule under the Thomas's right rule. These steps, they are the same as the TSO protocol. When we consider this write C, then under the Thomas's right rule, this write C is ignored and this read B is possible because a newer transaction is now trying to read a value updated by an older transaction, and here also we see that this is a read B. So, this will be executed. Hence, we see that this schedule is possible under the Thomas's right rule, but not under the timestamp ordering protocol. Thank you.